All right. When we finished part one of the OpenMP notes, we were here. Let's continue on. Okay. Probably the biggest use of OpenMP is to parallelize for loops. For loops are great, right? You can generalize equations and then repeat them over and over without having to write out an equation a million times. Okay. And that makes it perfect for parallel too, is you want to do the same code, but on different parts of your data. So here's how we would do that. We'd pound include, we'd set the number of threads to whatever we wanted it to be. And then we say pound pragma OMP parallel, just like we did back here, but we add one more word to the directive, for. Pragma OMP parallel for, and we immediately follow it up with a for statement. Immediately. Okay, so now the compiler knows, take this for loop and break it up among however many threads I've got. So this one pragma creates a team of threads and then assigns some of the for loop passes to each thread. So this is great. Now, what's this default none? In a moment, we're going to talk about shared and private variables. Like let's say we have a variable declared up here and we use it in the for loop. Do we want each thread to have its own private copy of that, or are they all writing into the same one? Okay. But default none means there's not a default to that. So anytime you've got that, where you've defined it or declared a variable up here, but use it in here, it's going to whine. Whereas if you leave default none out, there is a default, and I don't even remember what it is, shared or private, but you don't want it defaulting. You want to deliberately, strategically decide what to do. The other thing to know is this end of the for loop right here. There's an implied barrier, and a barrier is a place in your code where all threads have to get to before any of them are allowed to continue. They're all going to wait at the barrier. There's an implied barrier right here. You can turn that off if you want, but typically you want it because you want all these values available for whatever the code's going to do next. All right, rules for loops. They're not really all that stringent, but there are some. First of all, this index must be an int or a pointer. That makes sense. It can be, for loops can have a float as the index, but it's not advised. If you're going to expect this to be parallelized with OpenMP, that's got to be an int or a pointer. The start and terminate must have compatible types. The start and terminate conditions cannot change during the execution of the loop. And the reason is this pragma is going to generate some extra parallel code based on what start and terminate are right now. And so if you go change them inside the for loop, that's going to mess that up. Okay. The index can be modified, only be modified by this. So in the middle of the code, you can't say index plus plus. Okay. You can only change it here. There can't be interloop data dependencies. And this is an interloop data dependency. In normal single-threaded programming, this works fine because we've already computed I minus 1, and in the next pass, we want to use that to compute I. But in parallelism, imagine thread 0 had all the iterations up to here, and thread 1 has all the iterations starting here. Well, the first thing thread 1 is going to do is do this, but that doesn't exist yet because thread 0 hasn't gotten around to computing it yet. Now, all of these things are required for OpenMP to parallelize your for loop without messing up, but it doesn't actually print any messages about it. It's up to you to know it, and especially this one. It's up to you to know about interloop dependencies and make sure you don't do them. Also, there's a slightly reduced list of ways you can tests for termination, and there's a slightly reduced list of ways you can change the index in between for loop passes. Okay, now here we get back to the default none. So let's suppose we define a variable up here, we declare it, and now we use it down here, we assign to X. What does that mean? When I break this for loop up into chunks to give to each thread, does that mean they're all writing into the same variable? And what does it mean when multi-threads are all writing into the same variable? So if you don't want that to happen, out here on the pragma line, at the end, you say private X, the variable name. And that means it will magically, secretly create an X for every thread. If you say shared, then that means it's the same X for every thread. And again, this is why I recommend default none, because if you do this and you get it wrong, or you just let it default and I don't even remember what the default is, then bad things could happen. OpenMP won't flag any errors. It'll just quietly mess up. Because of the loop dependencies, this kind of thing is not parallelizable, because this line, x of I equals x of I minus 1 plus 1, that's an interloop dependency. So, and OpenMP won't flag this as a problem. It'll just quietly mess it up. But if you want to do that, you do something called for loop fission. Fission means to break something apart. And so you do one for loop with the thing that can't be parallelized, and then you do a second for loop with the thing that can be parallelized. Okay. Collapsing. What if you've got two nested for loops? Well, which one do you put the pragma on? You can't put it on both. Well, what you do instead is you say, you punt and you say collapse two, meaning OpenMP will magically put the pragma on both of these combined. Okay, how many for loops to collapse into essentially one loop? So that's really helpful because this is a pretty common design pattern. Single program, multiple data. Excuse me. In single program, multiple data, we do a pragma OMP parallel, but not a for. Excuse me. We ask here, and this is a private variable, we ask it, which thread am I? We ask it, how many total threads are there? And then we say, okay, do the work. This is known as single program, multiple data. Essentially, it's roll your own for loop. And so each thread will execute this do work. But it's computing what it needs to do itself. So I know how many threads we've got. I know which one I am. I'll figure out what my role in all of this is. Hey, how do you actually allocate for loop passes to threads? There's two ways. One's called static, one's called dynamic. Static means you're going to take all the for loop passes and divide them up into certain number of threads right from the start. Okay, each thread has a certain number of for loop passes it's in charge of. The flaw in that plan is, what if one of the threads finishes before all the others? Well, now you're wasting compute power. What you would rather do, if you think there's going to be a difference in how long each thread takes to execute its tasks, is you allocate part of the for loop passes to the threads, leaving some in a pool. And then when a thread goes idle, it gets to pluck some out of the pool. Okay, and so this is called dynamic threads. And you can set this on the pragma line. And so at the end of the pragma line, you say schedule, static, schedule, dynamic, and then you have something called chunk size. And chunk size, well, I think of this as dealing cards at a poker table. And so let's say we had 12 for loop passes and we had 3 threads, contrived example. Okay, if I say static comma 1, that means I'm going to deal 1 for loop pass to thread 0, 1 to thread 1, 1 to thread 2, then this one to thread 0, this one to 4, this to 5, then this one to thread 0. And the advantage of that is if, say, the lower for loop passes are expected to run quicker than the upper ones, then this spreads it out. Okay, this gives each thread some lower ones and some upper ones. If you say 2, well, then it's going to deal 2 cards to thread 0, 2 cards to thread 1, and so on. And if you say 4, then it's going to deal 4 cards to thread 0. And that's what chunk size is all about. If you do nothing, if you say like schedule static and don't specify a chunk size, it'll do this one. It'll do 1. Okay, but think about this as dealing cards like the famous dogs playing poker paintings. All right, that's the end of number 2. Come on back to number 3 and we'll wrap up our OpenMP notes.